start today's session with Saghar Hosseini, who will take us from anomaly cancellation in string theory to symmetry descent in QFT. Take it away.
Thank you for the introduction, and thank you so much for the invitation. Thanks to the organizers for arranging this very nice workshop. So today I'm going to tell you about a few different papers which are related. The first one is about symmetry TFT, worked on together with Fabio Aperuzzi, Federico Bonatti, Iñaki Garcia-Echeverria, and Sakura Safrinameki. And then another work which is related, work with Iñaki Garcia-Echeverria, and finally a more recent work with Yuji Tachikawa and Hauser. So first, let me give you some motivation, tell you about what's the story behind these papers and how they're related, why they followed from each other. So it all started from trying to understand generalized symmetries. So recently there is a lot of interest. There has been a lot of interest in trying to understand these symmetries. A lot of you have already worked on it, and there are different ways to try to learn about them. There is field theory approach, just purely field theoretic way to try to understand them, and we can also start from a string theory, and then we can try to see how they arise in different constructions. Now, for me, when I started my PhD, there was this paper by Iñaki from 2019, and the way I tried to learn about them was starting from a string theory. So we ended up trying to learn about them also with Michele. We had some papers about how they arise in various different theories. For example, in 4 dimensions, in Agios-Douglas theories, in various 5-dimensional theories. We started from M theory. And the way it works is that the way that it works is that when in string theory you have branes and they can wrap different cycles. When they wrap cycles, so if you try to start from a string theory and put it on a manifold which is non-compact, so it extends to infinity, and then you can wrap branes on these cycles which extend to infinity, and you get objects which are defects, and these are charged under the symmetry. So if you study the topology of this boundary geometry of your geometry, you can learn about symmetries. And this naturally led us to think about symmetry theory, because when you start from a string theory and you put it on the boundary geometry, then you can come, so say you start from a string theory, you put it on some geometry, you get a d-dimensional QFT. But then if you put this string theory on the boundary geometry rather than the whole geometry, you get a d plus 1 dimensional theory. And this theory is supposed to explain explain all the symmetries and different anomalies that you can have in d dimensions. So very much like anomaly theory. And so in this work, we try to obtain this symmetry theory by dimensional reduction. And the way we try to do it was to reduce so to get the actual theory, symmetry theory, an equation for it. So there are different ways to do it. Maybe you could just study all the operators in this symmetry theory, see how they end on the boundary, or if they generate symmetries in the bulk. But you can also try to get an action for it. And to do that, what we did was to reduce the supergravity effective action on this boundary geometry. And this gave us some action for the symmetry theory. Now, this was not quite perfect because we were missing some information. So in a string theory, the fields are self-dual, or there are fields that are dual to each other. And when you study a QFT or its higher form symmetries, there are always, like, if you have a p-form symmetry, you can find a symmetry that's dual to it. And this was not, the supergravity action doesn't capture this self-duality. So what we had to do was try to redo this. So in the paper by me and Iñaki, earlier we tried to see how to get this missing information, and we tried to construct an action for a string theory which captures this self-duality. And this has to be done in differential K theory or K theory, KO theory or K theory, depending on which string theory you're looking at. And actually, it's interesting to know that some of this missing information could be found from different approaches, like using ADS-CFT. There is this paper which explores it in that sense. So, yes. 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 Yes, so I mean, in differential KO theory, we basically doing this democratic formulation where we sum over all the RR fields. Yes. Sorry? Well, we'll get to it. Yes.
There are no problems for the concept one. The issues arise only from concept one.
Well, so we would like to think of the democratic formulation where we sum over all these different fields in a string theory, and the whole field is self-dual when you sum over it. And that's, I think, the correct way to think about it. But because in string theory, even if you don't want to think about self-duality, if you take a field, there is always a dual to it, and this is not captured by the supergravity action. And that was our problem. So we tried to do this in differential KO theory, but there was a lot of subtleties and there was a lot to learn. We didn't actually do it fully in differential KO theory with Iñaki, and we did some KO theoretic action. Then later, in the paper with Yuji and how we tried to do the whole thing in differential KO theory, but we didn't actually get to study symmetry TFT from it because it turned out to be an interesting problem on its own. So let me explain why. So when we try to write an action for the self-dual KO valued RR fields, we can't do this in 10 dimension. We need to go to 11D for reasons I will explain. Now, the modern, also on the other hand, we know that in modern description of anomalies, we can understand them as a higher dimensional theory that, I mean, we can explain anomalies by writing a TQFT in one higher dimension. And it turns out that this 11-dimensional action that we want to construct for a string theory to describe these self-dual fields is actually the anomaly theory for a string theory. And of course, there should be no anomalies in a string theory. And there is, for example, in type 1, we have the Schwarz anomaly cancellation. And this is captured by this bulk action. So not just the perturbative anomalies, but also we can show that there are no global anomalies in string theory. And I will talk about that in a second. So my talk is split into two parts. The first part, I want to talk about how this bulk, we can construct this bulk action for the RR fields, and then how this describes anomaly cancellation. And in the second part, I would like to tell you about how we can reduce this bulk action to get the symmetry theory. So to do this, I will first talk about why we have self-dual fields in a string theory, and what is this KO theory or differential KO theory that I'm talking about. How we can construct an action, it should be in terms of a quadratic refinement, for reasons we will see. And then this can be done in various string theories. This was done in this paper for type 2 string theory. And but type 1 is more interesting because there is Schwarz anomaly cancellation. So this is what we did in the paper, and I will go over this one. This can be generalized to other string theories like Sugimoto and Sagnotti string theory as well. Finally, I will go over how to reduce this action to get the symmetry theory via an inflow and look at some examples. So, okay, so I tried to also summarize. So sorry, I don't know if my slides are very clear. I thought it would be nice to write them by hand, but maybe it turned out a bit messy. I don't know. So so this is just summarizing what I'm going to talk about. So we construct the 11D action. We have a choice of quadratic refinement, choice of cohomology theory, which is K or KO, depending on which type 1 or type 2 string theory we consider. And we can cancel the perturbative anomaly using this bulk action. We can also see that global anomalies cancel. Then we do the dimensional reduction. We find the higher dimensional theory describing the symmetries and anomalies via inflow. Okay, so why do we need a bulk? Well, it's always hard to write an action in even dimensions for fields that are self-dual. An easy example that's perhaps a more familiar example is the 2D chiral boson. It has when we say a field is self-dual, we mean that this field strength is dual to itself. So for a chiral scalar, we have d phi equals the star of d phi, and it's one approach to describe this system is to try to couple it to a gauge field, as was done in this paper. So we changed the action by this coupling term, then we can, for this gauge field that we couple to, we can write a spin-Chern-Simon action in 3 dimensions. So we go into 1 dimension higher to describe to describe this bulk mode as an edge mode of this Chern-Simon theory. And if we go to string theory, so in type 2b, for example, we have C0, C2, and C4 are fields. Usually people just say DC4 is a star of DC4 and C4 is a self-dual field, but this is not quite true. We should really be using K-theory classification of RR fields, and there we have a sum of all the fields, RR fields. So we have C0, C2, and C4, and they're also dual. So C8 is dual to C2, and C6 is dual to C4. So we sum over all of them. And in type 1, we just have the C2 and C6 field, which we sum over again. So now if we take C as such, then D of C is equal to a star of D of C here. And we can just write an action for this because it would vanish because of self-duality. So what we need to do following these papers is to write a Chern-Simon action in 11D, which describes this self-dual fields as edge modes. Okay, so how I also said that this block action describes anomaly cancellation. So let me quickly go over. Let me review quickly the anomaly cancellation in type 1 theory. So we know that in type 1 we have fermions are gravitino, dilatino, and gaugino. We can describe their anomalies by this anomaly polynomial, where R is the curvature and for the metric, and F is the field strength for the gauge field. So this is type 1 SO32 gauge theory. And we know that these anomalies of fermions can be cancelled by this Green-Schwarz mechanism. So the field C2 and C6, they couple to D1 and D5 branes will field the strengths H3 and H7. And these H3 and H7 have modified Bianchi identities given here. Now we can cancel these fermion anomalies by writing an action where we couple to B2 field, and the variation of the B2 field in the action will give us a x4 times a y8 term, which exactly cancels this I12 anomaly polynomial. So, okay. And now, how do we try to see this anomaly cancellation? Well, first, we need to talk about why we want to do it in KO theory. Well, there are these papers where they discussed that D-branes should be classified by K theory in type 2. And for us, there are many definitions of K theory. For us, it's natural to take the definition where K theory group is given by a topological class of a pair of complex bundles, ENF, on some space M, which it is a class defined by this equivalence relation. So if you add another bundle to E and F, these two classes, these two pairs are equivalent to each other. And this is very natural to describe D-branes because the E and F are nothing but the complex bundles that you define on the D9 and anti-D9 branes. And this equivalence relation is where a pair of branes cancel and you can add them in this manner. So similarly, the RR fields that you're interested in, they are classified also by K theory with a degree shift that comes from some long exact sequence. So in type 2b, the RR fields are classified by K minus 1 of M. In type 2a, they're just classified by Km, and in type 1, they are classified by K also. Instead of complex bundles, here you have real bundles, because when you do the projection from type 2b, you just get the real bundles. Now, we want to write a bulk action for these RR fields, right? So we need to encode various information. One is the K theory data, the fact that they're classified by RR fields, and we want to know about the topology. But we also want to know about the local anomalies, the perturbative anomalies, the I12 anomaly. Now, so to do this, we just don't need just KO theory, but differential K theory. So this differential part tells us about the differential forms and the curvature part. So how do we do this? First, we need to define a bilinear pairing that maps the differential KO classes multiplied by differential KO classes to another differential KO class. From that, we need to construct a holonomy function, which is U1 valued. So because remember, we want to construct a Chern-Simon theory in 11D. So we need a U1 valued pairing. And this must be gauge invariant quantity. Then we can define the bulk action as a quadratic refinement of this pairing. Now, what is quadratic refinement? So it's just given by this definition here. So if you have this pairing, a quadratic refinement is one that satisfies this equation. Then we can write the action in terms of it. So why can't we just take our action to be this pairing of A with itself? Well, this holonomy function is U1 valued, and it's not an invertible phase, so it cannot be the anomaly theory for our string theory. So we actually need to construct this quadratic refinement. So we can actually see this is invertible by taking some other S action in terms of B, and then by defining A to be A prime plus B. Well, that takes a few steps. We can show that that S and S prime are inverse of one another, so S is indeed invertible. Yeah.
Very nice question. Q of 0 is not 0.
We take the condition where it has to be 0 so that we can uniquely determine. That helps us uniquely determine the quadratic refinement.
What would be the interpretation if it was not 0?
So Q of 0 would only depend on the metric, and if we don't set it to 0, I think we run into a problem where the quadratic refinement is no longer uniquely defined. So when this A is a dynamical field and we pass integrate over, and when we do that, we end up with some, I think, some function of metric.
I can think of Q0.
Yes, yeah. Sorry, it's very complicated. I'm not sure if I can explain it. Okay, so I was just telling you how we can construct the action. Now I need to define exactly what I mean by this differential KO theory class A. So this A in K theory, so in differential K theory, I put this kind of hat to mean differential K on K, and we can take a representative of this A to be a triplet VBC. So V here is a complex bundle which is valued in K of M. B is a connection on V, and we can write this chain character, which is a form of even degree. And then there is also this C. This C is a differential form of odd degree. And this C is actually what gives rise to the RR field. When we look at the gauge transformation of C, there are gauge degrees of freedom, and we see the RR fields in 10D as edge modes of this C. So if we take two different triplets, then these two, they can represent the same A if they satisfy this condition. So we say that they are gauge equivalent. They must be related in this manner. So here B tilde is the homotopy between B and B prime. So B is defined in this interval at 0 and B prime at 1. And then you integrate over this. This A hat is the A roof genus, and the integral of this should give us the difference between these two C's. So we can define gauge equivalence in this manner. And the quantity that is gauge invariant is the field strength of this A, which we define as chain class of B plus DC, chain character of B plus DC. So if you try to look at either of these triplets, they give the same R of A if they are equivalent by this relation. Now, to define this Q, we need to define this holonomy function first. And this holonomy function, in the complex case, so in the K theory case, it's defined in terms of the eta invariant of the Dirac operator. And in terms of, so this part by the APS index term, we know we can write it in terms of the connection B that we had. And this part depends on C in the triplets that we have. So now that we have these, we can go ahead and find the quadratic refinement. Okay, and now the difference between differential K and KO is that in differential KO, we here, this should be V. V is a real bundle. And sorry, this should be also V, this should be V. And B is a connection on this real bundle. And now instead of the chain character, we have the Pontryagin character. And it's just a real version of it defined this way. And again, we have the gauge, the field strength, which is a gauge invariant quantity. So to see the R fields as the edge modes, what we need to do is to determine the boundary conditions. To see them, we must take the boundary condition where A on the boundary of this 11D bulk theory is given by some background field A, which we can set to 0. And this is the class that is set to 0 or to A. So we can do gauge transformations of this A, and those degrees of freedom, those don't vanish on the boundary, and those are precisely what give us the R fields. So if you take A to be in K0, then B would be shifted by 1 degree, which is the gauge degree of freedom, which is where we expect the R fields to be classified in type 2B. So, and to see that we have a self-dual field on the boundary, we should add an action for this a kinetic term to this action that we had Q of A, and the action is this kinetic term is given by the fieldless in terms of the fieldless strengths of A. So now if we look at the equation of motion of this action, we can, and then we want to take an ansatz for this fieldless strength for A near the boundary to have this form. So it is given in terms of some H, which turns out to be the R field. So near the boundary, we are taking Y11 to be of the form of an interval times x10, and at tau equal to 0, we have the boundary. So we reproduce that, make sure this answer satisfies this boundary condition. Now, if you look at the equations of motions of this action and then substitute these answers in it, we find that this field H is self-dual, and that it has this modified Bianchi identity, which is what we expect for the for our R fields. So it depends here. It would vanish for the type 2B case, and it doesn't for type 1. Okay, so what is actually this Q of A? So we wrote before what the holonomy function was, and we can define the quadratic refinement in terms of it to be this function. There are 2 parts. There is again the part which is given in terms of the eta invariant. This is actually depends on the connection on the bundle, and this connection is related to the gaugino. So this is actually the anomaly of gaugino. And there is the C-dependent part. And this is what we take to be the anomaly theory of the RR fields. So for the anomalies to cancel, what does it mean in 11D? It means that under gauge transformations, this action should be gauge invariant. So there is no anomalies on the boundary. So the gauge transformation, we discussed them before. So we could take 2 different representatives of this A, and if this action is gauge invariant under this transformation, then that means our action is anomaly free. Our theory in 10D is anomaly free. So what is X here? So in this paper, it was worked out that X is given by square root of A hat times Chern character of B. Now, what about type 1 theory? So this type 1 theory is more interesting because we will see how Green-Schwarz anomaly cancellation arises from this action. So in type 1, this is just, I'm summarizing, we have this little C in this triplet is C3, C7 plus C11 in the bulk. And this is the fieldless strengths. The action is given by some eta invariant plus this part that depends on C. So what is X in this case? So if you remember, I just said that in type 2B, in that paper, it was worked out that X is a square root of A hat Chern character of B. So we tried to first take X to be a square root of A hat Pontryagin character of B for type A, but it doesn't quite work. So if we look at the action, it wouldn't be gauge invariant if we take this X. if you just take this x, then only some parts. So the variation of the eta is given, so it's in the adjoint representation of the gauge group, and it's given by this quantity, and this x only cancels this part of this gauge variation, and this part is not cancelled. So we can try to take an ansatz and see what works for the cancellation of this part. And it's only the metric dependent part that's the problem. So we can take this FR and then see what it can be for the cancellation to work. We must satisfy this condition, and then we can work it out what each of these, in each degree it must be. Did I actually write it here? Sorry. So the x that we find in this form is equal to, so for x4 it's equal to twice the x4 in Green-Schwarz, and for y8 is equal to, sorry, for x8 is equal to x8 of the Green-Schwarz. So I called it y8 before, sorry. And well, the reason for the difference here with multiplication by 2 is that the quantization of the C field, C3 field, is different in K theory and cohomology. If you integrate DC over a 4 cycle, in K theory, the quantization is different because of how the mapping between K and KO theory works. So this is not inconsistency. And in fact, F0, so X0 would be just F0, which is 32. And this tells us the rank of the gauge group has to be 32. And if we do some further computation, we can actually we see that differential KO theory tells us the gauge group has to be SO32. So it's kind of a different derivation that we see the gauge group has to be 32. Again, this is by anomaly cancellation, so it's the same story, but from a different perspective. And remember that the total anomaly so for the anomaly cancellation, the total anomaly of the fermion was equal to x4 times y8. And in our action, we only have the anomaly of the gaugino. So when we look at the variation, there will be some metric dependence terms left, and those exactly cancel the anomaly of the Gravitino and Dilatino. So just by the gauge invariance, we are forced to have these kind of extra quantities which exactly belong to Gravitino and Dilatino. So it's like we were just doing differential KO theory, and it kind of seems to know about the field content of a string theory, or should we say that string theory knows about this differential KO theory formulation, which is, I think, is very interesting.
Get the E8.
Which E8?
The E8 plus C8. Get the this way.
Sorry, which E8?
Yeah.
The chaotic E8 plus C8.
Oh, okay. No, so this is doesn't apply unfortunately to heterotic string theory, just type 1 and type 2 string theory. For heterotic, the classification is given by topological modular forms, and it's different story.
Some different formally.
Yes, yeah, it doesn't work for heterotic. So there are fields. I mean, there are no R fields. There's no classification by differential chaos. So this brings me to part 2 of my talk. So now we have seen that anomalies indeed cancel from this bulk perspective, and this can be generalized to different projections of type 2b, so to Sagnotian Sugimoto string. Okay, so now how do we actually see symmetries coming from this anomaly theory for string theory? So now going to symmetries, remember that I will start with this simpler example. We have choices of symmetries. So for this super Yang theory with Lie algebra U2, we can have different choices of one-form symmetries. We can have Z2 one-form electric symmetry or magnetic symmetry or dionic symmetry. We cannot have all of these at the same time. As you know, the defects charged under these symmetries, they are not mutually local in the theory. So we cannot realize all of them at the same time. And these different choices, they can be captured by a theory in 5 dimensions, 1 dimension higher, which we call symmetry TF theory. This is nothing but the BF theory. And here you have the gauge fields B and A, and different boundary conditions for this gauge field, they give us these different choices. So now, more generally, in higher dimension, the same story applies. If you have a p-form symmetry, you'll always going to have a d minus p minus 4 form symmetry dual to it. And again, these different choices can be captured by a BF theory in one higher dimension. And this is a non-invertible theory. That's why you have different choices. And on this side, you have a gap boundary, which again, you choose boundary conditions for B and A and reproduce all these possible choices of symmetries that this theory on the boundary can have. So this is before fixing the choice of the symmetry, we call this a relative theory. And once we have a choice, a fixed symmetry, this becomes an absolute theory. Now, if we do have anomalies, how does it work? So in the case that we have the fixed symmetry G for this theory tau, we usually describe the anomalies by an anomaly theory in 1 dimension higher. It's an invertible TFT. Now, what if we haven't fixed the choice of symmetry for this theory on the boundary? Then we can have different possible symmetries, and the anomalies we cannot describe by anomaly theory. We need a non-invertible theory to describe it. So more generally, we have what we call a symmetry theory, which knows about all the possible symmetries and anomalies of this relative boundary theory. And this, again, if sometimes it's not possible to fix this gap boundary, like in 62, 0 theories, you cannot always have an absolute theory. So if it is possible to pick boundary conditions and fix this symmetry for the relative theory, then you end up with the anomaly theory and a boundary theory with a fixed symmetry. So this is the idea of symmetry theory. And we would like to obtain this from a string theory. How does that work? So in a string theory, let's say we put string theory on some product space X times Mn, and we geometrically engineer some quantum field theory, maybe conformance quantum field theory, quite possibly. And we take this X internal space to be a non-compact manifold. So particularly, usually we take it to have this form of a cone over some link L, which is, so it extends to infinity. So this L goes to infinity, basically. And it's a Calabi-Yau manifold. So when we reduce on Mn, on X, sorry, we get a quantum field theory of dimension N. Now, to get the symmetry theory, what we want to do is to put the string theory on L times y n plus 1. So this y here is n plus 1 dimensional, and L is the boundary geometry of this Calabi-Yau. And when we reduce string theory on L, we get a n+1 dimensional theory, which is the theory that describes the symmetries and anomalies of this QFT that we had before. Now, before I was saying that we tried to, in this paper, reduce the supergravity action to get this symmetry theory. But again, we didn't see all the terms here, including especially the BF term, which I was telling you about, tells us about the choices of symmetries. And so we tried to reconstruct the action in terms of differential KO theory or K theory to see these additional information. So in picture, we try to first reduce the string theory on L to get the symmetry theory, but this doesn't work. So what we do, we extend this 10D theory to an 11-dimensional theory. So we extend Y to Z, and then this Z times L is 11-dimensional, and then we can integrate on the boundary geometry to get a theory which descends to, via inflow, descends to this theory, symmetry theory Y. So, so if we look at the gauge degrees of freedom here, they will give us the D of the sim TFT. So what's the difference between anomaly inflow and symmetry inflow? So we are generalizing the idea, and here when we have an anomaly theory, this is for a d-dimensional QFT is a d+1 dimensional theory, and here B is a background for the symmetry G of the d-dimensional theory. And then we can write the anomaly polynomial, which is given in terms of the variation of the anomaly theory, which again is in terms of this classical background field B. But in the symmetry theory construction, the symmetry TFT action, it depends on a dynamical field beta. And the 2+ dimensional action, which I call S inflow, this depends also on a dynamical field, different field B. And the way that B and beta relate is that B is beta are the gauge degrees of freedom of this B. And it is in this way that we can find the symmetry TFT from this one higher, well, 2 higher dimensional action of this when we do the dimensional reduction. So the change in the gauge transformation of this action, of the inflow action, give us D of the sim TFT. Okay, so there are many examples to consider. In the paper that we had with Yuji and Hao, we didn't actually have time to look at any symmetry TFT action. We just focused on trying to understand anomaly cancellation from differential KO perspective. But there are, I think, many interesting directions to go from here. And one thing we did look at was try to see how we can reproduce the invertible phase of a 9D theory by reducing type 1 and S1. And so more generally, we can try to understand discrete anomalies from the reduction of this eta in lower dimension. So for example, there are 8 DSPN theories which arise from putting the 7 branes on O7 plus branes, and they have some discrete anomalies which are very subtle, studied in this paper, and we are trying to also understand how we can write a TQFT describing these anomalies, which was not possible to find before, but we should be able to do it from this construction. Now, there are many other examples to consider. For example, in the paper with Iñaki, we only looked at this part of the KO action, and this tells us about the BF theory or sometimes mixed with anomalies in lower dimension, and we should be able to reproduce these results from reducing the eta invariance again in the bulk action. And another interesting fact to note is that these categorical symmetries that we have all been studying, the idea is that the symmetry generators, they are not in a single dimension, but they combine. And this K-theory formulation naturally fits into that idea. So starting from this action, we should be able to see these arising, the higher groups and non-invertible symmetries mixing. So I try to, for the purpose of this workshop, I try to look at an example of these Quiver theories. I didn't get very far. I tried to look at something that has been done before. There was this nice paper by Michele Rosotto and Kentaro Mori trying to study two group symmetries of little string theories, and they construct this from F theory, but we know from these papers by me as well that we can obtain these little string theories from type 1 string theory by putting it on C2 mod gamma to get various Quiver theories. And so for a fixed number of NS5 branes and D5 branes, we get this Quiver gauge theory. And a simple example is for having two NS5 branes and no D5 branes, and we get SP2 gauge theory. So I'd like to reproduce the two group symmetries from this construction. So in this 60 theories, there are one-form symmetries associated to the center of this gauge group, and there is also zero-form continuous symmetries which are associated to gauge and gravitational currents. These give rise to the two group in 60. And this is also already not so hard to see that we did have these. So if we write out the type 1 action in terms of the components of this C, we have this Y8 and X4, which when we reduce, exactly reproduce those currents in 60, which give us the higher group symmetries. So to reduce this action, we put Y11 on W7, which describes the symmetry theory of the 60, times the boundary of this Calabi-Yau. And reducing this action, we get some terms where there's B3 cup delta B3. So the B3 is a field in 7D now. And there are other terms which tell us about mixed Luft anomalies of 0-form and 4-form symmetry, for example. But these two terms, they give us the equation of motion in 60 that should lead us to get the two group symmetry in 60. So I think this was just one simple example, and it should be generalizable to more theories, whatever your preferences are, and I would be happy to discuss anything you have in mind. Now, also, I didn't look at the reduction of the eta invariant. We know how to reduce it on the boundary of this geometry, already done in this paper. So, but I like to think about what it means in the 60 theory when we reduce it. Now, there are other interesting examples to consider. We could also look at other brane constructions or even ADS-CFT setups. How can we study symmetries, or just even if it doesn't have to be just categorical symmetry, general symmetries, we could study just anomalies of R-symmetries mixed with global symmetries. I mean, these have been studied before, but now perhaps we could formulate it in a more precise manner and understand various anomalies in lower dimensions from this construction. So another thing that we need to do is to generalize the case of type 2B to be twisted differential K theory, because there is a twist by the B field, and many anomalies or symmetries, they come from having the B field in the action. And this can be understood using SQM, interestingly, which is something we are thinking about also. And always it's interesting to match these symmetries across dualities in higher and lower dimensions. So that's another way we could continue. So to summarize, I construct an invertible anomaly theory for string theory, describing anomaly cancellation. It also, we also didn't go into details, but tells us that the gauge group has to be SO32 in type 1, and there is no gauge group in type 2b. So it's nice to see it all works as we expected. And finally, I talked about how we can reduce this action to study symmetries and anomalies in lower dimension. That's all I have to say. Thank you.
Questions?
So there are also like similar formula for the d-brane central charge. They're like integral over a rho square. Like there is an a formula where one writes like square root of a rho of genus times the Chern character. But then one can argue that actually the correct formula, instead of the square root of a rho of genus, you have to have this gamma class. So I wonder if the gamma class plays any role in your story. Shouldn't like you also replace this square root
Sorry,
of?
I'm not sure I understand you.
Well, my short question isn't, shouldn't like you replace the square root of a rho of genus with the gamma class?
A gamma class.
Yes.
Maybe I'm not sure.
Yeah.
Questions? So I have more of a broader question, like how many anomaly theories are known if we're looking at string theory constructions of quantum field theories, like stuff like this? Like what's left? Like you showed some things, but are there like so now you did type 1, for example, like is there stuff that's like not attainable at all with current methods, or?
I'm not so sure. Probably there are always field theoretic methods to also study these anomalies. But one example that I mentioned was the anomaly in 8DSPN theories. There are some discrete anomalies which people tried and couldn't find some TQFT description for, and this seems to be the way to study those.
Okay.
Yes.
And my question was more like, what's still left from the stringy perspective? Like, which string theory setups can you not do an anomaly theory for yet? Because it seems
just
like
a string theory, not lower dimensional. You mean just string theory, not
yeah. In general, like from string theory, anything that can be constructed in string theory as a QFT, can you get the anomaly theory using these methods? Is that the way to think?
No, I mean, not all the theories are constructible from a string theory that we
Yeah. That's what I mean. What's inside of string theory? Can all of this be done that's in string theory?
So you're saying what is left to do?
Yeah. Like if we live in string theory.
Yeah.
Anything I can do with string theory, can I also produce anomaly theory now? Or other like setups where it's not known how to get anomaly theory?
Okay.
Because like, for example, now you showed like how to, in type 1 and so on, get anomaly theories. Like, are there still pieces left? Like, for example, heterotic is this?
Yeah, it's a bit different in heterotic.
Okay. I can also ask one.
I'm not so sure.
So you mentioned you are able to do the dimensional reduction and get the symmetry theory for generalized symmetries. I think if I'm not mistaken, you mentioned higher form and higher group. Is it also the case for the non-invertible symmetries? Did you manage to find the?
I haven't looked at any examples now, but I think in principle it should be possible. I mean, you know, a lot of these, almost all these non-invertibles we see in all the papers, they are obtainable from just higher form symmetries through gauging and SPT phases. So in principle, the data is there to construct them that we obtain from a string theory. But also, we have seen pairs where from the full brane action, we get the non-invertible symmetries. So actually, the brane action, we should also try to write in differential KO theory and reduce it there to see the non-invertibles that come from there.
More questions? If not, let's thank Saghar.
Okay, thank you.